to the organizers for giving me this opportunity to speak here. This talk is going to be about this remarkable formula that you see on this slide. This is a quote from Ray Reiter's 1980 paper called A Logic for Default Reasoning. It's called the frame default, and I'll explain in a minute what it's supposed to express. And we'll talk about this very dramatic story of this formula, about what happened to it over more than 20 years. In particular, we'll see what happened in 2001 when this mathematical formula turned into a piece of code. This rule that you see here, it looks like a prologue rule, but actually it's designed for an execution process that is very different from what prologue does. It is a quote from the program called the RCS USA Advisor. RCS stands for Reaction Control System, and that was the system aboard the space shuttle that was used to change the orientation of the shuttle in flight. And USA stands for, not for what you think, in this case USA stands for United Space Alliance, and that is the company that at that time was responsible for the management of the space shuttle fleet. And the RCS USA Advisor was the program used to verify that the design of this reaction control system was such that it would work even in the case of multiple failures of various, if several parts of the system malfunction at the same time. This program was written by a group of researchers who continued the work that Ray Reiter started in 1980, the work on the frame default, in collaboration with engineers from United Space Alliance. And we'll talk about this piece of code too. What this talk is not about, it's not an attempt to describe the history of the frame problem. It's only a very, very small piece. There are lots of important ideas not related to what we are going to discuss. And some of the sources where you can find more information about other important work on the frame problem, there are listed here 4 books where these ideas are discussed in detail. The frame problem, as you all know, is a problem of describing dynamic domains in such a way that we would not have to specify explicitly the conditions that are not affected by executing an action. And here is a very simple example illustrating the frame problem. So imagine that we are talking about 2 individuals and just one property. An individual can be in the room or outside. And what we know is that Alice is initially in the room and Bob is not. And I describe this information using this predicate symbol in, with the argument, with the subscript 0 indicating that we are talking about the initial state. Alice is in the room initially, Bob is not. And then this action is executed, Bob enters the room, and that is expressed by this atomic formula here, enter Bob. And then we also have a general law saying that expressing the effect of this action of entering the room. Any person who enters will be in the room after that. And you see here the implication which describes this law. X is a variable for people. And you can notice that in here has the subscript 1, because here we're talking about time 1, the time after the execution of the action. And what we would like to conclude from these 3 assumptions, what common sense tells us, is that after Bob entered the room, now both Alice and Bob are going to be in the room. We'd like to conclude in 1 of Alice, in 1 of Bob. And the second formula logically follows. It follows from the second and third bullet by just applying predicate calculus rule. Oops. What did I do? The first formula asserting that L is in the room at time 1 does not follow because we don't have any assumptions here relating the values of the predicates in 0 and in 1 for the same argument. And that's an instance of the frame problem. We want this fact that the location of Alice is not affected by Bob entering the room. We would like it somehow to be incorporated to be incorporated in our description of the domain. And this frame default that I showed a minute ago, it was Ray Reiter's attempt to solve the frame problem. This default is written in the language of Reiter's default logic. What Reiter proposed is that to formalize domains like this, instead of just classical first-order theories, sets of axioms expressed in first-order logic, we'll use something more general, default theories, that in addition to axioms, may include what Reiter called defaults. And the default, you can think of a default as a generalization of an inference rule. You can, if you look at this picture here, H is the conclusion that we derive by this generalized inference rule. F1 through Fm are first-order formulas, premises, from which H can be derived. And what we have after this column, that's really what makes this a default rather than just an inference rule. We have also a list of formulas, first-order formulas G1 through Gn. Each of them in Reiter's paper is prefixed by the symbol M, which is like a model operator. And what these justifications tell us is that we allowed to derive H from F1 through Fm only under the assumption that these justifications, G1 through Gn, can be consistently assumed. Now, this explanation that you see here in parentheses about the meaning of this default really makes very little sense. We need to explain what we mean by consistently assume, consistently with what. And what Reiter had in mind is that it should be possible to consistently to assume these justifications without a contradiction with the set of all facts that can be derived from our axioms using classical logic and all the defaults included in the theory. And this is really a circular description because in explaining how these rules work, we refer to the set of facts that can be generated using these rules. And Reiter's major accomplishment was in his ability to make this idea precise. And we'll not talk now about how he did this, but he managed to give a precise definition of when a formula is a theorem of a default theory. He was able to make the turn this intuitive explanation into a precise definition. And if we go back to this example, when we want to express this idea that the value of the predicate in remains the same when you move from time 0 to time 1, unless the value of in is fluent, in was affected by an action. This is what can be expressed by these two defaults. The first default says, from the assumption that x is in the room at time 0, you can derive that x is in the room at time 1 if this can be consistently assumed. If the action that was performed between time 0 and 1 was affected the location of x, that could be an exception of this default. But by default, if there's no contradiction, we can assume that x is still is still in the room. And similarly, if we know that x is not in the room at time 0, if this is consistent with all the available information, you can conclude that x is not in the room at time 1. And this is what you see here next in this on the slide is a generalization. If R is a fluent, then to express this idea that the truth value of R, if R was true at time 0, then by default you can assume that it's true at time 1. This can be expressed by this formula here, by this default in Reiter's formalism. And this is actually almost identical to this quote from Reiter's paper that I showed before, to this frame default. If you compare this default with what you saw a few minutes ago, you can see that the difference here is really in that in my simple example, I used the simplest possible model of time. There are just two time instances, 0 and 1, and something maybe happened between them. And Reiter's formulation used a more sophisticated model of time. It essentially used the situation calculus model. Instead of the subscript 0, Reiter's formulation used the second argument s, which is a situation variable. This situation describes the state of the world at time 0. And instead of the subscript 1, Reiter used this term f of xs. And this is what this means is that a certain action, which action that was possibly dependent on this parameter x, when it was executed in state or situation s, f of xs is the resulting situation. So essentially, this default and this default express the same idea, except that I use a very simple model of time, and this is a situation calculus default. 6 years later, another approach to the frame problem was proposed. In John McCarthy's paper on applications of circumscription to formalizing common sense knowledge, he introduced what he called abnormality theories. An abnormality theory is essentially a first-order theory that uses a special predicate, ab. Ab of x means x is abnormal. And in addition to arbitrary models of our abnormality theory in the sense of classical logic, we can talk about the minimum models, the models of the theory in which the extent of ab, the set of all abnormal objects, cannot be made smaller without violating the axioms. In this paper on abnormality theories, McCarthy showed how to express this idea of minimality by a second-order formula called circumscription. He needed second-order predicate variables because when you say that the extent of a certain predicate is minimal, what you mean is that it's impossible to make this predicate smaller. So you talk about modifications about other possible predicates. So you need second-order formulas to express this idea. And just as Reiter's default logic was a general approach to talking about defaults, which in particular Reiter applied to the frame problem. Similarly, this idea of abnormality was a general approach talking about defaults, and what McCarthy proposed is to solve the frame problem by writing this axiom here. If actually what McCarthy used was situation calculus expressions like those used by Reiter, but what I show here is something similar to his approach for the simplest possible model of time, which is two time instance 0 and 1. McCarthy's solution to the frame problem was writing a formula like this: if x satisfies R at time 0 and x is not abnormal, then x satisfies R at time 1. Now, the major difference one major difference between what Reiter did in 1980 and what McCarthy did in 1986 is that McCarthy tried to apply his solution to a simple toy example. We usually, when we see a certain general idea applied to toy examples, we often say, well, it's just a toy example, we need to see how it scales up. McCarthy's example was a toy example, but in Reiter's paper in 1980, there were no examples at all. He wrote this formula, which obviously looked nice, but he didn't try even to do this Alice entering the room thing. And this was a remarkable thing that McCarthy decided to try a specific example. Actually, the domain to which he applied his solution to the frame problem was the blocks world, in which blocks can be moved and painted. So the interesting example of the frame problem that this domain allowed us to talk about is that if you move a block, its color does not change. If you paint it, its location does not change. Something that McCarthy did in this paper, he didn't really try to automate reasoning about circumscription. But at least he tried to verify his conclusions about the effect of circumscription using a proof checker that could work with second-order logic. So he verified some examples of use of circumscription using this proof checker, but the examples involving his solution to the frame problem, that was too complicated for his experiments. He was not able to do this, so his solution to the frame problem, along with some other examples, remained unchecked, but just as Reiter's frame default, they looked plausible. Some other work that was done around that time, around 1986, there was some work done on the cases when the second-order formula describing circumscription can be written equivalently as a first-order formula. And some work was done even on doing this automatically. And that was a little step towards automating reasoning about circumscription. A little step because, well, first of all, because these methods were not applicable, unfortunately, to McCarthy's solution to the frame problem. His abnormality theory for that case was much too complicated. And secondly, even after you rewrite circumscription as a first-order formula, automated reasoning in first-order logic is also very difficult, so it was little stuff. But the really interesting thing that happened also in 1986 is something that Leora mentioned in her talk this morning. Two researchers from Yale University applied circumscription to a domain which is much, much simpler than the blocks world. It was so simple that they were able to figure out what really happens when you apply circumscription. There are two examples really sufficiently simple, and it turned out that it doesn't work. Even if you restrict attention to minimum models, you cannot draw the conclusion that you wanted. So 1986 was a bad year for all people interested in knowledge representation. Lots of papers were published in various ways to fix the problem, and there were many discussions about how general these solutions are. What I'd like to mention is one development that very quickly followed, which was kind of different in spirit from the approaches advocated by Reiter and McCarthy. In this explanation closure approach to the frame problem, it was different from the others in that it was not based on any general theory of default reasoning, such as default logic of circumscription. The possibility that was investigated during several years, beginning in 1987, was to look at the syntactic form of the axioms that we usually write to describe the effects of actions. And again, this work was done in the framework of the situation calculus, but in our case, we are going to use again, a very simple model of time and see what happens in this case. Here was our effect axiom. For every x, if the action enter x is executed, the fluent in of x holds at time 1. And if we assume that these axioms describing the effects of actions have a certain specific syntactic form that is actually used in many examples, maybe what we can do is we can figure out how to automatically generate, on the basis of a set of effect axioms, everything that is missing that is needed to solve the frame problem. So that's an approach that is less ambitious than McCarthy's and Reiter's, because it does not rely on any general theory of default reasoning. But the hope was that maybe that approach would work. And specifically, one formulation of this approach was think in terms of explaining changes that you have observed in the world. Think of this fluent in of x. If its value changed, if in is true at time 1 but was false at time 0, that means that something happened to change the value of this fluent. And if the only effect axiom to have in our theory that affects the value of the fluent in is enter, then the only possible explanation is that this action enter of x was executed. So the idea of this explanation closure approach is to describe a syntactic process that turns a set of effect axioms into extends it by adding a set of corresponding explanation closure axioms, and in the presence of the explanation closure axioms, the frame problem would be solved. And that works very nicely, and for this reason, For this reason, 1987 was a particularly unpleasant time for the frame default. Just as in 1980, no attempt had been made by that time to use the frame default for even a toy domain. Its close relative circumscription, for which this has been done, was found inadequate because of the CL shooting example. There had been no attempt to automate reasoning in default logic, and this idea of explanation closure, instead of using a general theory of default reasoning, looked pretty successful. So maybe this idea of the frame default did not work and was even unnecessary. That was a bad time, but that was also the time when things started to change. I'd like to talk now about some developments that, well, the first of them was related to default logic, but it was not clear at that time that it would somehow help, would be somehow related to resolving difficulties with the frame default. What we learned in 1987 is that default logic has an important application, very different from its attempted use to solve the frame problem. It turned out that default logic helped us to solve an important theoretical problem in logic programming. That was the problem of the meaning of negation in Prolog programs. What you see here is two rules written in Prolog, where in the second rule this negation is failure operation is used. The strange symbol \+ is used in Prolog to as a negation sign, because its shape is similar to the derivability sign, which is cross. So it means not derivable. And what these rules are supposed to express in Prolog is that A has the property P. The first rule is fact, and the second rule says if A has the property P and there is no way to prove, there is no evidence that B has a property P, then C has a property P. So when you run this query P of X, what Prolog will tell you is that there are two possible values of X for which that satisfy P. The first value is A and the second value is C. And what happens when Prolog works is that, first of all, your Prolog system will notice that we have this fact P of A, so you can take X to be A, and P of X will be true. And then it will try to use the second rule to find another value of X which satisfies P. And the rule tells us that we need to do two things to establish P of C. First of all, we need to establish P of A, but we have done this already. And second, we should determine that there is no way to prove P of B using these rules. So Prolog will try to prove P of B. And that is obviously impossible because P of B doesn't even occur in the heads of rules. It does not match the head of any of these rules. So Prolog will say P of A succeeds, P of B fails, so the negation of P of B succeeded, so P of C can be derived and will be done. So this is what happens inside, but people interested in the semantics of Prolog, they asked, is there any kind of more declarative way of explaining the meaning of Prolog programs? Can you explain in what sense this is a correct answer to the query P of X, other than just by explaining what's happening inside when you run Prolog? And one remarkable idea that several people at that time came up with was that you can think of Prolog rules with negation as alternative notation for defaults in the sense of writer. And for defaults, writer had the semantics. So by using this translation, we get a semantics for negation in Prolog. And according to this translation that was proposed, when we look at a Prolog rule, we think of its head, like P of C in this case, as the conclusion of the default. We think of the atom P of A as the premise because it's not negated. And since P of B is negated, we will not treat not P of B as a second premise, but rather we'll use it as a justification. So we understand this rule as the default, allowing us to derive P of C from P of A if the negation of P of B can be consistently assumed. And it turned out that this way of giving a precise meaning to Prolog negation really correctly describes the behavior of Prolog. If this SLDNF procedure, which is used in the process of operation of Prolog, gives the answer yes to a ground query, that means that this ground query is a consequence of our logic program in the sense of writer's semantics. And that was a remarkable accomplishment. What happened soon after that is that this view was developed according to which logic programs of some kind can be essentially used as simply abbreviation for default theories. So according to this answer set semantics of logic programs as it was defined in 1990, a logic program consists of rules of this form. Here every L sub I is a literal. An atom with this classical negation sign. This classical negation sign was not available in Prolog, but this relationship between Prolog and default logic suggested that it would be a nice addition to the syntax of rules. And then in the body of the rule we can have these literals and also some literals with the negation is failure symbol before it, which is similar to what was denoted by this \+ in Prolog programs. And according to the answer set semantics for logic programs, such a rule has the same meaning as a certain default. And what you see happens in this default is that the head of the rule turns into the conclusion. The literals that are not prefixed by negation as failure are viewed as premises, and the literals that are prefixed by negation as failure are put in this justification part of the default. Every literal here is replaced by its complement, the complementary literal, to reflect the negative aspect of this not. And also each of them is prefixed by this model operator M as in writer's logic. So in particular, if you look at these defaults for the frame problem that we looked at before, this is what they will be presented as in this syntax of extended logic programs. One other thing that happened when this answer set semantics was produced is that instead of saying, well, this is just a shorthand for default and you should read writer's paper to determine what the semantics is, what was done by the inventors of the semantics is they simply took writer's definition of the semantics of default logic and reformulated it in greatly simplified form, as it turns out, for the special case of the defaults that correspond to logic programming rules, so that the concept of an answer set was inspired by writer's definition of an extension for default logic, but it was formulated directly in terms of logic programs instead of explicitly referring to this translation. You can say that nothing important really happened at this point, because essentially what is a answer set semantics? You simply we're simply saying, when we want to use the answer set semantics, that we want to use a subset of default logic, defaults where all the premises and justifications and conclusions are literals, and use a slightly different syntax for it. Not a big deal. Why is it important? But there were several reasons why actually this was an essential development. One of them is that this just the switch to this logic programming syntax emphasized similarities between the work on the frame problem on the base of default logic and parallel developments that led to the invention of the calculus of events. That was a logic programming based approach to the frame problem. Writer's frame default and the calculus of events are very different approaches to the frame problem. But what we learned from this work on the relationship between logic programs and default logic, and from switching to this new syntax, is that their logic basis is almost the same. One other reason why the answer set semantics was essential and not merely a reformulation of a subset of writer's logic is that the very idea that we want to use write rules, write defaults in this logic programming syntax requires that we only use as axioms and as parts of defaults, we only use literals, not more complex formulas. And that encourages a certain change in the style of logic representation. Even if you look at our very simple example, this axiom here that we use to express the effect of the action enter is actually a more complicated formula than what can be expressed in answer set programming. It's an implication. So if we want to redo this example that we looked at in the syntax of answer set semantics, we would have to use, instead of this formula, this rule here, logic programming rule without negation is failure. But what this rule actually represents semantically is something that is slightly different from this formula. It's not an implication, it's an inference rule. It's a default without justifications. And in this case, it's not very essential, but sometimes switching from implications to inference rules, the easy part of the default logic, was essential. And yet another reason why this work on reformulating default logic in terms of logic programming style rules was important is that it turned out that Prolog can be viewed as a partial, very, very partial, but still partial implementation of default logic. One of the problems with default logic was, until that time, that we didn't have any implementations. So what we learned in 1987 is that there's no need to work on implementations. It's available, it's been available for a long time. You just need to rewrite your default theory in some cases in a special syntax and then just run Prolog. So if, for instance, we take our example, so what you see here in the first line are three literals corresponding to, actually identical to the axioms that we had in our first example. In the second line of this logic program, you can see our description of the effect of entering a room written in the syntax written as a Prolog rule or as an inference rule. And then writers frame default written in the syntax of logic programming. And what you have here is a logic program that is almost ready for execution. If you really want to write it in the syntax of Prolog, this is what you have to do. Besides some trivial things like using capital letters for variables as Prolog requires, and not using subscripts, so because we want an ASCII file. And switching from NOT to this \+ plus. One slightly more essential change we have to do is we have to replace this classical negation symbol, which is not available in Prolog, by just a different predicate. Instead of the classical negation of in 1, we write out 1. There is a slight difference. Sometimes there are cases when the negation of a predicate cannot be simply seen as an entirely different predicate out. There's a slight difference, but in this case, the difference is really not essential. You can think of the classical negation of in 1 as simply a new predicate. So if you wrote this program in the syntax of Prolog and give this query in 1 of x, you'll happily see x equals Bob, x equals Alice. They're both in the room at time 1. We'll see without any additional implementation work that at least in this special case, the frame problem was solved correctly. Unfortunately, Prolog has turned out to be a partial implementation of default logic, not only in the sense that defaults have to have very simple, literal justification, premises, and conclusions, but the other reason was that often Prolog doesn't terminate. Doesn't really produce an answer to your query, and that happens in some important cases. If you look at this default theory here, which has two defaults, no axioms and two defaults. One says that if P can be consistently assumed, then P can be derived. If not P can be consistently assumed, then not P can be derived. This is a theory which, according to writer's semantics, has two extensions. There are two ways to interpret it. You can think of P and know its logical consequences as true assertions, or you can think of not P and know its logical consequences as true assertions. If you write this default theory as a logic program, you get these two rules. And according to this answer set semantics, which is a simple reflection as a set of writers' semantics, it has two answer sets. One is the atom P, the other is the negative literal not P. But if you try to run Prolog, this is what this program will look like in the syntax of Prolog. If you give this query P instead of an answer, you get an error message. It can be very different error messages depending on the kind of Prolog that you use. Sometimes it says out of local stack. Sometimes it just dies. In the old time, Prolog will just die. But you will not get a meaningful answer. And what is worse is that it's not even clear what kind of meaningful answer you can expect from Prolog. Since there are two possibilities, P can be true and P can be false. When you give a ground query to Prolog, the only thing, there are two things that Prolog can do if it gives you an answer. Say yes or no. What would it say in this case? Would not be even clear. So in that sense, Prolog was a very, very partial implementation of default logic. The next thing I'd like to mention is a development that seemed to be completely unrelated, even unrelated to, not related to logic programming, to default logic, but which turned out to be crucial. It's the invention of the use of set solvers. In 1992, we learned that if you want to generate a plan of a fixed length for a given planning problem, you can think of this as the problem of finding a truth assignment that satisfies a certain set of clauses that can be generated from your planning problem. And then you can take a set solver and just run it, and maybe it will produce this solution. And this seems like a rather trivial observation. Of course, every problem in class NP can be represented as a problem of finding a truth assignment for a set of clauses, and then, of course, you can try to run a set solver on it. But the reason why this was, there were two reasons why this was a major event coming up with this idea. One reason is that we learned from the paper on planning and satisfiability how to encode a planning problem by a set of clauses, not just in polynomial time, but in a very compact, efficient way. And second, 1992 was the beginning of this period of amazing growth of improvement in the quality of the computational procedures used in set solvers. So every year, set solvers could solve more and more complex problems, and there was a time in the late 90s when in planning competitions, these kind of planners that were based on simply translating a planning problem into SAT and then running the best available set solver would work better than specifically solutions developed specifically for planning by people who try to use ideas related to planning. So that was why this paper had a tremendous effect on planning and the whole research. And the next thing that we learned that showed us how the progress in the design of set solvers was related to writers' work on the default. It turned out that the computational methods and ideas that were used in the design of efficient set solvers could be applied also to the problem of generating answer sets of a logic program. So what we got is what is called answer set solvers. These are systems that are pretty much like set solvers. That is, they in principle, the algorithms that we have, that in principle they always terminate. They don't do what Prolog does. And just as a set solver, if you give it a set of clauses that has several satisfying interpretations, can produce, if you instruct it to do so, all of them, an answer set solver can do the same thing. If you give to it a logic program with several answer sets, it will produce any one or all of them. And I can say that this task of extending the methods used in the design of set solvers to the problem of calculating answer sets, I can say it was actually not just moving it to a different domain, but that was applying, I would say, the algorithms used for solving SAT to a more general problem. Although both problems are in class NP, in a certain precise sense, the language of logic programs under the answer set semantics is more expressive and computation than the language of clauses. And if you actually want to take a set of clauses and rewrite it in the form of a logic program so that its answer sets would correspond to solutions, you always get very simple answer set programs of a very simple kind. This work, it involved not just moving these problems to different domain, but moving them to, in a certain sense, more general, more difficult problem, and they worked wonderfully. And you can see the difference between what Prolog does and what answer set solvers do with the program here. If you take the first example here, you do not have to give a query to an answer set solver. You just give the program, and it says there's one answer. The answer set consisting of P of A and P of C. In other words, what an answer set solver will give you is the list of all ground atoms to which Prolog would have said yes. And if you give to an answer set solver a program to which Prolog would have said out of local stack, an answer set solver does something very similar to what set solvers do. It gives you the list of two answer sets, two extensions in the sense of writing. And we can combine, as we learned essentially at the same time in 1997, very early when the first answer set solvers were, when the first answer set solver was created. At that time, I think we had just one called S models and created in Helsinki. At that time, these two ideas, the idea of converting planning problems to SAT, and the idea of extending SAT to a subset of default logic were combined. So what we learned at that time is that you can take writer's default theory describing an action domain, formalize it slightly differently, because if you want to find a plan of length n, you have to use a slightly more complex model of time. Instead of just talking about time 0 and 1, you have to add a variable for time, and you can think of the values of this possible values of this variable as numbers from 1 to n. So instead of these rules that you saw before, you would write rules like this. You would, instead of saying in 1 of x, you would say in of x holds at time t1. So this is the rule that, with this slightly more sophisticated model of time, we describe the effect of entering, and this is what the writer's frame default looked like in 1997. And if you it was pretty straightforward at that time. We could see that you can take essentially writer's style description of an action domain plus a description of the initial state and the goal, and get this logic program to give to an answer set solver, and it will give you a solution pretty much in the same way as set solver gives you a solution, except that you don't have to describe your domain by a set of clauses. You can describe the domain exactly, almost exactly, the way writer wanted in 1980, as a default theory of the kind that corresponds to a logic program, and computational process will work. And now we can come back to the example from this RCS USA advisor. This slide shows how little it gives you the wrong impression that two examples and real-world applications are very close to each other. There was a lot of work, of course, involved in the design of this RCS USA advisor that I don't show to you, but here you see the writer's default as we used it in the toy example here, and here's its counterpart in the real-life program. What you see here is that instead of talking about X being in the room, we talk about the fluent that was of interest for describing this system. And this NH corresponds to the classical negation of holds, which is represented as a new predicate. So it's a very straightforward translation of this into the syntax of Prolog, with replacing the toy fluent in of X by the real-life fluent value of WX. Now let's go back to this ideal explanation closure axioms that made, at least as it seemed in 1987, the use of default logic unnecessary. There was a good reason why the designers of the RCS USA Advisor founded their logic program on writer's ideas rather than explanation closure axioms. Explanation closure axioms work fine, but they have a limitation which played a crucial role when you talk about systems as complicated as the reaction control system. You remember that what we need to apply the explanation closure idea is an assumption that the effects of actions are described by axioms of a certain special syntactic form. What happens often happens in more complex domains than our toy example, in particular in the reaction control system, is the case when the sum of the effects of actions are described indirectly. So to enhance our toy example here, imagine that what we want to add to our simple example is that whenever Bob is in the room, if he at the same time holds his cell phone in his hand, then the cell phone will be in the room also. Then the action of Bob entering the room under some conditions, if Bob didn't leave his cell phone in his car, will also indirectly affect the location of the cell phone. And if you describe the effects of actions in this two-step manner, by specifying some effects explicitly, and also by specifying some information on the relationships between different fluids, so that other effects, indirect effects, would follow logically, then generating explanation closure axioms for this more general syntax becomes more problematic. But for writer's idea, for the use of default logic, there is no difference. Just write corresponding rules and everything will work automatically. There's no need to change anything. And this problem of describing actions with indirect effects is sometimes called the ramification problem. So to sum up what I just said, this idea of the frame default handles the ramification problem, or I can say the frame problem in the presence of ramifications, better than the explanation closure idea. And this is the last slide I wanted to show to you. Let's look at what we just discussed from a more general perspective. Just as set solvers became something a lot more significant than tools for creating efficient planners. They are good for any kind of combinatorial search. In the same way, the use of ANSYS set solvers for solving the frame problem, to now just one small example of something a lot more general. This ideas that we talked about, they're an example of what is called ANSYS set programming. This is generally the use of logic programs under the ANSYS set semantics for knowledge representation and the use of ANSYS set solvers for search. I can almost say, as far as the first part of this is concerned, using the ANSYS set semantics for knowledge representation, I can almost say the use of default logic for knowledge representation. That would not be very precise, because what happens in the input languages of existing ANSYS set solvers that are used now in ANSYS set programming is that we first replaced default logic by its subset, when we have literals instead of complex formulas. And then instead, we invented several additional constructs. We extended the syntax of these logic programs by additional constructs that are not covered, that are in the spirit of writer's default logic, but they're not covered by writer's definition. For instance, programs became disjunctive. And this is not similar to anything that writer did. He didn't have disjunctive defaults. Various aggregates were added and so on. So I would say that what we are doing in ANSYS set programming is a modification of default logic. We made it smaller applied the ideas, computation ideas inherent in the design of set solvers, and then extended this by additional constructs that were not available in Reiter's system. Currently, there is only one book, as far as I know, which is about answer set programming, but I learned recently that very soon we'll have 2 more books on answer set programming. So I just learned recently from Thorsten Schaub that he and his collaborators will give us a book in a few days. Thorsten. Or in a few weeks. Submit. Okay. And Michael Gelfond tells me that he and his co-author are planning to publish a book next year. So these are 3 areas that contributed more than others into the creation of this new area of answer set programming. So that's a kind of a more general view on what happened to Reiter's frame default. Thank you for your attention.